Tonight's topic is the universe's mysteries, dark matter, dark energy, and cosmic expansion. Thanks for listening, and let's begin. Part 1. The Hidden Universe. Welcome to this comprehensive exploration of the universe's greatest mysteries, dark matter, dark energy, and the cosmic expansion that shapes everything we observe in the night sky. As we begin this journey, let yourself settle into a comfortable position, allowing the vastness of cosmic scales and the gentle rhythm of scientific explanation to carry you into relaxation. The universe we observe with our telescopes, the stars and galaxies that fill our night sky with light, represents only a tiny fraction of what exists. Current measurements indicate that ordinary matter, the atoms and molecules that make up stars, planets, and everything we can directly observe, constitutes merely 4.9% of the universe's total energy content. The remaining 95.1% consists of mysterious components we cannot see directly, dark matter and dark energy. This realization emerged gradually through decades of astronomical observations and theoretical work. In the early 20th century, astronomers believed that the visible universe represented essentially everything that existed. Galaxies were collections of stars, and the universe consisted of these galaxies scattered through space. The notion that the majority of the universe might be composed of something entirely different from ordinary matter would have seemed absurd to most astronomers of that era. The story of how we discovered the hidden universe is a story of careful observation, unexpected measurements, and the willingness of scientists to accept that our universe is far stranger than it appears. It is a story still unfolding, with new observations and experiments continuously refining our understanding, while simultaneously revealing new puzzles and questions. The discovery of dark matter. Early observations. The first hints that something unseen might exist in the universe came from observations of galaxy clusters in the 1930s. Fritz Zwicky, a Swiss astronomer working at the California Institute of Technology, was studying the Coma cluster, a large collection of galaxies located approximately 320 million light-years from Earth in the constellation Coma Berenices. Zwicky was measuring the velocities of individual galaxies within the cluster using spectroscopy, a technique that analyzes the light from distant objects to determine how fast they are moving. When light of a moving object is analyzed, its wavelength appears shifted depending on whether the object is moving toward or away from the observer. This shift, called the Doppler shift, is the same phenomenon that causes the pitch of a siren to change as an ambulance passes by. By measuring the Doppler shifts of light from galaxies in the Coma cluster, Zwicky could determine how fast each galaxy was moving. He found that the galaxies were moving remarkably quickly, with velocities of hundreds or even thousands of kilometers per second. This discovery was surprising, but what made it truly puzzling was these velocities implied about the cluster's mass. For galaxies to move at such high velocities while remaining bound together in a cluster, rather than flying apart into space, the cluster must contain an enormous amount of matter. The gravitational attraction of this mass holds the cluster together, preventing the fast-moving galaxies from escaping. Zwicky calculated how much mass would be required to gravitationally bind a cluster where galaxies moved at the observed velocities. The result of this calculation was startling. The amount of mass required to hold the cluster together was approximately 400 times greater than the mass visible in the form of stars and gas in the cluster's galaxies. Either the galaxies were moving so fast that the cluster should be flying apart, which clearly was not happening, or the cluster contained vast amounts of matter that did not emit light and could not be directly observed. Zwicky called this unseen matter Dunkel Materie, German for dark matter. He proposed that the missing mass existed in some form that did not produce light, making it invisible to telescopes, but nevertheless present and exerting gravitational influence on the visible galaxies. This was a radical suggestion, and many astronomers were skeptical. Perhaps Zwicky's measurements were wrong, or perhaps there was some alternative explanation for the high velocities that did not require invoking vast amounts of invisible matter. For several decades, Zwicky's dark matter hypothesis remained controversial and was not widely accepted. The observations of the Coma cluster were difficult to verify, and it seemed more likely that some error in measurement or analysis had led to the surprising result, rather than that the universe contained enormous quantities of a previously unknown form of matter. Vera Rubin and the rotation curves of galaxies. The evidence for dark matter became much more compelling in the 1970s through the work of Vera Rubin and her colleagues, who studied the rotation of spiral galaxies. Rubin was an astronomer at the Carnegie Institution of Washington who specialized in measuring the velocities of stars and gas within galaxies. Spiral galaxies, like our own Milky Way, consist of a central bulge of stars surrounded by a flat disk containing spiral arms. The disk rotates around the galactic center, with stars and gas following roughly circular orbits. By measuring how fast material at different distances from the galactic center is moving, astronomers can determine the galaxy's rotation curve, a graph showing orbital velocity as a function of distance from the center. The expected shape of a galaxy's rotation curve can be calculated based on the distribution of visible matter in the galaxy. In the central regions, where most of the galaxy's stars are concentrated, orbital velocities should increase with distance from the center as material encounters the gravitational pull of more and more mass interior to its orbit. Beyond the central bulge, in the outer disk where star density is lower, orbital velocities should decline with increasing distance, following the same pattern that planets in our solar system follow, with outer planets orbiting more slowly than inner planets. Rubin and her colleague Kent Ford developed techniques to measure rotation curves with unprecedented precision. They used spectrographs attached to telescopes to analyze light from different parts of galaxies, determining velocities at many points from the galactic center out to the visible edge of the disk. Their measurements were painstaking, requiring long exposure times and careful calibration, but they produced rotation curves of exceptional quality. The rotation curves Rubin measured did not match theoretical predictions based on visible matter. In the inner regions of galaxies, the rotation curves followed expectations, with velocities increasing as expected from the concentration of stars in the galactic bulge. However, in the outer regions, rather than declining as predicted, the rotation curves remained flat or even continued to rise slightly. Stars and gas in the outer parts of galaxies were moving much faster than could be explained by the gravitational pull of visible matter. This pattern appeared not in one or a few galaxies, but in essentially every spiral galaxy Rubin and her colleagues observed. The flat rotation curves seem to be a universal property of spiral galaxies, indicating a systematic discrepancy between the distribution of visible matter and the distribution of gravitating mass. The most straightforward explanation was that galaxies are embedded in large halos of dark matter extending far beyond the visible disk. The dark matter halos required to explain flat rotation curves are immense, typically extending to distances several times larger than the visible galaxy and containing several times more mass than all the visible stars and gas combined. The dark matter is distributed in a roughly spherical halo, with matter density declining gradually with increasing distance from the galactic center. This distribution produces a gravitational field that causes outer regions of galaxies to rotate faster than would be predicted from visible matter alone. Rubin's observations, combined with similar work by other astronomers during the same period, provided compelling evidence that dark matter is real and represents the majority of matter in galaxies. Unlike Zawicki's earlier work on galaxy clusters, which involved measurements of entire clusters and could potentially be affected by various complications, Rubin's rotation curves came from observations of individual galaxies and showed a clear, consistent pattern that was difficult to explain except through the presence of dark matter. The acceptance of dark matter as a real component of the universe marked a major shift in astronomical thinking.
The realization that most of a galaxy's mass is invisible fundamentally changed how astronomers understood galaxy formation and evolution. It raised profound questions about the nature of this dark matter. What is it made of? How does it interact with ordinary matter and light? And how did it become distributed in the halos we observe?
The nature of dark matter. What could it be? The discovery that dark matter exists raised immediate questions about its composition. What kind of matter could be present in such enormous quantities, could exert gravitational influence on visible matter, but could not be detected through the emission or absorption of light? The first possibility considered was that dark matter might consist of ordinary matter in forms that do not emit significant light. Astronomers use the term baryonic matter to refer to ordinary matter made of protons, neutrons, and electrons, the particles that make up atoms. Baryonic matter does not necessarily emit light. Objects like planets, asteroids, brown dwarf stars too small to sustain nuclear fusion, black holes, and other compact objects consist of baryonic matter but may be difficult or impossible to detect directly through their light emission. The hypothesis that dark matter consists of massive compact halo objects, or MACOs, suggested that galaxy halos might be filled with Jupiter-sized planets, brown dwarfs, or similar objects. These objects would exert gravitational influence but would be too faint to detect individually at galactic distances. Surveys were conducted to search for MACOs through a technique called gravitational microlensing, where a dark object passing in front of a background star temporarily brightens the star's light through gravitational focusing. Microlensing surveys conducted in the 1990s and 2000s observed millions of stars over extended periods, looking for the brief brightening events that would indicate a dark object passing in front of them. The surveys did detect some microlensing events, confirming that some MACOs exist in galaxy halos. However, the frequency of events was much lower than would be required to explain all dark matter. MACOs might contribute to dark matter, but they cannot be the dominant component. Additional constraints on baryonic dark matter come from observations of the cosmic microwave background and measurements of element abundances from the early universe. The processes that produced light elements like deuterium, helium, and lithium in the first minutes after the Big Bang were sensitive to the total amount of baryonic matter in the universe. Measurements of these element abundances, combined with observations of the cosmic microwave background radiation, provide an independent determination of the total baryonic matter density in the universe. These measurements indicate that the total amount of baryonic matter in the universe, including both visible matter in stars and gas and any dark baryonic matter that might exist, is insufficient to account for the dark matter inferred from galaxy rotation curves and other observations. The total baryonic matter density is approximately 17% of the total matter density, meaning that roughly 83% of matter in the universe must be non-baryonic, composed of something other than ordinary atoms. This realization led to consideration of exotic forms of matter that might exist but have not been detected in laboratory experiments. Particle physicists had proposed various hypothetical particles that might be produced in the early universe and might still exist today. If such particles interacted weakly with ordinary matter and light, they could pass through normal matter without leaving detectable traces, making them difficult or impossible to observe directly despite being present in large quantities. The leading candidate for non-baryonic dark matter is weakly interacting massive particles, or WIMPs. These hypothetical particles would have masses considerably larger than protons, perhaps tens or hundreds times the proton mass, but would interact with ordinary matter only through gravity and the weak nuclear force, one of the four fundamental forces of nature. The weak interaction is much feebler than electromagnetism, allowing WIMPs to pass through ordinary matter with minimal interaction. WIMPs are attractive dark matter candidates for several reasons. Theoretical calculations suggest that if WIMPs were produced in the Big Bang with properties matching those predicted by certain extensions of the standard model of particle physics, their abundance today would naturally be close to the observed dark matter density. This coincidence, sometimes called the WIMP miracle, suggests that WIMPs might provide a natural explanation for dark matter. Extensive experimental efforts have been undertaken to detect WIMPs directly.
These experiments use large detectors made of extremely pure materials, cooled to very low temperatures and shielded from cosmic rays and other backgrounds deep underground. The detectors watch for the extremely rare events where a WIMP from the dark matter halo passing through Earth might scatter off a nucleus in the detector, depositing a tiny amount of energy that can be measured. Despite decades of increasingly sensitive searches, no conclusive WIMP detection has been achieved. Experiments have ruled out WIMPs in certain mass ranges and with certain interaction strengths, constraining the properties WIMPs could have if they exist. The lack of detection has led some physicists to consider alternative dark matter candidates, though WIMPs remain a leading possibility. Another class of dark matter candidates is axions, extremely light particles that would be produced in large numbers in the early universe. Axions were originally proposed to solve a problem in quantum chromodynamics, the theory of the strong nuclear force, but they also happen to have properties that could make them suitable dark matter candidates. Axions would have masses billions of times smaller than electrons and would interact extremely weakly with ordinary matter, making them extraordinarily difficult to detect despite being present in large quantities. Experiments to detect axions use different techniques than WIMP searches. Some experiments search for the conversion of axions into photons in the presence of strong magnetic fields, while others look for effects of axions on atomic energy levels. Like WIMP searches, axion experiments have not yet produced conclusive detections, though they continue to probe parameter space where axions might exist. A more exotic possibility is that dark matter might consist of primordial black holes formed in the very early universe. Unlike black holes formed from collapsed stars, which can be no smaller than a few times the Sun's mass, primordial black holes could have a wide range of masses depending on when and how they formed. If primordial black holes with appropriate masses were abundant, they might constitute some or all of dark matter. Constraints on primordial black holes come from various observations. Gravitational lensing surveys limit how many black holes of certain masses can exist. The lack of observable effects from black holes passing through or near the solar system constrains their abundance. Current evidence suggests that primordial black holes cannot constitute all dark matter, though they might contribute to the total. The question of dark matter's composition remains one of the major unsolved problems in physics and astronomy. Despite extensive observational evidence for dark matter's existence and sophisticated theoretical models for what it might be, we still do not know definitively what dark matter is made of. This uncertainty reflects the fundamental challenge of studying something that interacts so weakly with ordinary matter that it has eluded detection despite intensive efforts. Dark matter distribution from galaxy scales to cosmic scales provides insights into its properties and its role in structure formation. Observations spanning from individual galaxies to the large-scale structure of the universe reveal patterns in dark matter distribution that constrain theoretical models and help guide searches for dark matter's identity. At the scale of individual galaxies, dark matter is distributed in roughly spherical halos extending far beyond the visible matter. The density of dark matter in these halos is highest near the galactic center and declines with increasing distance, following a profile that can be approximated by mathematical formulas. The exact shape of the density profile, particularly in the innermost regions, is still debated and has implications for dark matter's properties. One commonly used formula for describing dark matter halo density profiles is the Navarro-Frank-White profile, or NWF profile, named after the researchers who derived it from numerical simulations. The NWF profile predicts that dark matter density increases steeply toward the galactic center, diverging mathematically to infinite density at the center, though physical processes would prevent actual infinite densities from forming. Observations of galaxy rotation curves can test whether real dark matter halos match the NWF profile. Some observations suggest that dark matter density profiles in galaxy cores may be less steep than the NWF profile predicts, with dark matter distributed more uniformly in central regions rather than concentrated in a sharp cusp. This discrepancy, sometimes called the core cusp problem, might indicate that dark matter has properties different from those assumed in simulations, or it might reflect the effects of baryonic matter on dark matter distribution through processes not fully captured in simulations. The total mass of dark matter halos varies with galaxy size, with more massive galaxies embedded in more massive dark matter halos. The relationship between galaxy luminosity and halo mass can be studied statistically through various techniques, including satellite galaxy kinematics, gravitational lensing, and galaxy clustering. These studies reveal that most massive galaxies are embedded in halos containing up to 10 trillion times the Sun's mass in dark matter, while dwarf galaxies might have halos of only a few billion solar masses. The ratio of dark matter mass to visible matter also varies across galaxy types. Dwarf galaxies tend to be more dark matter dominated, with dark matter outweighing visible matter by factors of hundreds or thousands, while giant elliptical galaxies have smaller ratios, though dark matter still dominates by factors of 10 or more. This variation provides clues about how galaxies form and evolve within their dark matter halos. At larger scales, dark matter is organized into the cosmic web, a vast network of filaments and sheets surrounding large voids. This structure emerged from tiny density fluctuations in the early universe that grew over billions of years through gravitational attraction. Dark matter, being more abundant than ordinary matter and immune to radiation pressure that can counteract gravity, played the dominant role in establishing this large-scale structure. The cosmic web can be visualized through galaxy surveys that map the positions of millions of galaxies across large volumes of space. These surveys reveal that galaxies are not randomly distributed, but instead cluster along filaments and in dense nodes where filaments intersect. The regions between filaments are vast cosmic voids containing few galaxies. This distribution reflects the underlying dark matter structure, with galaxies forming where dark matter is concentrated. Computer simulations of structure formation that include dark matter reproduce the cosmic web seen in observations remarkably well. These simulations start with initial conditions representing the early universe and follow how dark matter clumps together under gravity over billions of years. The simulated dark matter distribution matches the observed galaxy distribution in statistical properties, providing strong evidence that dark matter drives structure formation. The largest dark matter structures are galaxy clusters, collections of hundreds or thousands of galaxies bound together by their mutual gravitational attraction. Galaxy clusters contain vast amounts of dark matter, with total masses reaching quadrillions times the Sun's mass. The dark matter dominates cluster mass by factors of 5 to 10 times compared to all the visible stars and gas in cluster galaxies. The distribution of dark matter in galaxy clusters can be mapped using gravitational lensing, a phenomenon where the gravitational field of a massive object bends light from background sources. When a galaxy cluster lies between Earth and distant background galaxies, the cluster's gravity deflects the light from the background galaxies, distorting their apparent shapes and positions. By analyzing these distortions, astronomers can reconstruct the distribution of mass in the cluster, including the dark matter. Gravitational lensing studies of galaxy clusters confirm that their mass is dominated by dark matter and show that the dark matter distribution is generally smooth and regular rather than clumped with the individual galaxy clusters. This distribution is consistent with dark matter particles interacting primarily through gravity rather than through electromagnetic forces that would cause dark matter to clump with galaxies more strongly. On the very largest scales, comparable to significant fractions of the observable universe, dark matter is distributed relatively smoothly, with density varying by less than 10 times from the mean density. This near uniformity reflects the fact that the universe appears homogeneous when viewed on sufficiently large scales, with structures like galaxies, clusters, and filaments representing relatively small perturbations on an otherwise smooth background. The evolution of dark matter distribution over cosmic time can be studied by comparing observations of the universe at different distances, which, due to light's finite travel time, correspond to different epochs in cosmic history. Distant galaxies observed as they appeared billions of years ago show less clustering than nearby galaxies observed in their current state. This evolution matches predictions from models where dark matter drives structure formation, with initially small density fluctuations growing into the structures we see today. Galaxy clusters and gravitational lensing serve as natural laboratories for studying dark matter, providing environments where dark matter's effects are magnified and can be observed through multiple independent techniques. The combination of different observational methods applied to galaxy clusters has provided some of the most convincing evidence for dark matter's existence. The mass of a galaxy cluster can be determined through several independent methods, each sensitive to different aspects of the cluster's mass distribution. The simplest method uses the velocities of galaxies within the cluster, following the same principle Fritz Zwicky applied to the Coma cluster. By measuring the distribution of galaxy velocities, astronomers can calculate how much mass is needed to gravitationally bind galaxies moving at the observed speeds. A second method analyzes the hot gas that fills the space between galaxies and clusters. This gas, heated to temperatures of tens of millions of degrees by the cluster's gravitational potential, emits X-rays that can be observed by space-based X-ray telescopes. The temperature and density distribution of the hot gas depend on the depth of the gravitational well it fills, which in turn depends on the total cluster mass. By mapping the X-ray emission from cluster gas, astronomers can infer the cluster's mass distribution. The third method uses gravitational lensing, already mentioned briefly. This technique has become increasingly powerful as observational capabilities have improved, allowing detailed mapping of cluster mass distributions. Strong gravitational lensing comes in two varieties: strong lensing and weak lensing, each providing different information about cluster mass. Strong gravitational lensing occurs when a galaxy cluster's gravitational field is strong enough to produce multiple images of a single background galaxy, or to stretch background galaxies into dramatic arcs and rings. These spectacular lensing features appear near the cluster center, where the gravitational field is strongest. By analyzing the positions and shapes of strongly lensed images, astronomers can constrain the mass distribution in the cluster core with high precision. Weak gravitational lensing produces more subtle effects, slightly distorting the shapes of many background galaxies across the cluster's field of view. While individual galaxy distortions are small and difficult to distinguish from galaxies' intrinsic shapes, statistical analysis of hundreds or thousands of background galaxies reveals patterns of coherent distortion that trace the cluster's mass distribution. Weak lensing is particularly valuable because it probes cluster mass over large areas, extending beyond the central regions where strong lensing occurs. When these three independent mass measurement methods are applied to the same galaxy cluster, they should agree on the total mass if measurements are accurate and interpretations correct. In practice, the methods do agree remarkably well, with typical agreement at the level of 20 to 30%, well within uncertainties expected from measurement errors and modeling assumptions. This consistency provides strong evidence that the mass inferred from these methods is real rather than an artifact of incorrect analysis. The comparison between mass measurements and the visible matter in clusters reveals the dark matter fraction. Approximately 85% of cluster mass is dark matter, with the remaining 15% split between stars in galaxies and hot gas filling the space between galaxies. Interestingly, most baryonic matter in clusters resides not in stars, but in the hot gas, which contains roughly twice as much mass as all cluster galaxies' stars combined. Some galaxy clusters have experienced recent collisions, providing unique opportunities to study dark matter's behavior. When two galaxy clusters merge, their different components interact in different ways. The galaxies themselves, being mostly empty space, pass through each other with minimal interaction, like bullets passing through a cloud. The hot gas in the two clusters collides and interacts through pressure and electromagnetic forces, slowing down and eventually merging. Dark matter, if it interacts only through gravity as commonly assumed, should behave like the galaxies rather than the gas, passing through the collision with minimal slowing. Gravitational lensing can map where the mass is after a collision, revealing whether it traces the galaxies or the gas. Several colliding clusters have been studied in detail, with the most famous being the bullet cluster. The bullet cluster consists of two galaxy clusters that passed through each other approximately 150 million years ago. X-ray observations show two clouds of hot gas that have been slowed and partially stripped from the clusters by the collision. Gravitational lensing maps show that most mass in the system is not coincident with the hot gas, but instead aligned with the cluster galaxies. This spatial separation between the bulk of the mass and the hot gas provides direct evidence that most mass is in a form that did not slow down during the collision, consistent with dark matter's expected behavior. The bullet cluster and similar systems provide some of the most direct evidence for dark matter's existence. Alternative theories that attempt to explain galaxy rotation curves and cluster dynamics without invoking dark matter generally cannot explain the bullet cluster's observed properties. The spatial separation between mass and gas seems to require that most mass exists in a form distinct from ordinary matter. Observations of galaxy clusters have also constrained dark matter's self-interaction strength. If dark matter particles could scatter off each other when they collide, this self-interaction would affect dark matter's distribution in ways that could be detected. Detailed studies of cluster collisions and cluster mass distributions have found no evidence for dark matter self-interaction, indicating that if it occurs at all, it is very weak. This constraint rules out certain dark matter models and helps narrow the range of possibilities for dark matter's properties.
The cosmic microwave background radiation, or CMB, provides an independent line of evidence for dark matter and reveals information about dark matter's properties from a completely different epoch in cosmic history. The CMB is light that has traveled through space for approximately 13.8 billion years, originating from a time roughly 380,000 years after the Big Bang, when the universe first became transparent to light. Before this time, the universe was filled with a hot, dense plasma of protons, electrons, and photons. The high temperature and density meant that photons constantly scattered off charged particles, preventing them from traveling far before being absorbed or scattered again. The universe was opaque, like being inside a thick fog. As the universe expanded and cooled, eventually the temperature dropped low enough that electrons could combine with protons to form neutral hydrogen atoms. With fewer free electrons to scatter photons, the universe suddenly became transparent. The photons that were liberated when the universe became transparent have traveled through space ever since, gradually losing energy as the universe expanded and stretched their wavelengths. These photons constitute the cosmic microwave background radiation we observe today. By studying the properties of this radiation, astronomers can learn about conditions in the universe at the time the light was emitted, providing a snapshot of the infant universe. The CMB is remarkably uniform, having nearly the same temperature, approximately 2.7 degrees above absolute zero, in all directions across the sky. However, precise measurements reveal tiny temperature variations, typically only a few tens of millionths of a degree, across different regions of the sky. These temperature variations reflect density variations in the early universe, regions that were slightly denser or less dense than average. The pattern of temperature variations in the CMB contains information about multiple properties of the universe, including its geometry, its total matter and energy content, and the relative amounts of different matter types. The detailed analysis of CMB data has provided some of the most precise measurements of cosmological parameters available, including the abundances of ordinary matter and dark matter.
The physics underlying CMB temperature variations involves the interplay between gravity, which tries to pull matter together, and radiation pressure, which resists compression. In the early universe, both ordinary matter and dark matter were present, but they behaved differently. Ordinary matter, being charged or able to form charged particles, interacted with photons and was subject to radiation pressure. Dark matter, interacting only through gravity, was immune to radiation pressure. Before the universe became transparent, regions where matter density was higher than average tended to collapse under their own gravity, while photons and ordinary matter in these regions were simultaneously pushed outward by radiation pressure. This created oscillations, with matter and radiation sloshing back and forth. Dark matter, unaffected by radiation pressure, continued to collapse gravitationally without oscillating. The oscillations of ordinary matter and radiation produced a characteristic pattern in the CMB temperature variations, with enhanced fluctuations at particular angular scales corresponding to regions where oscillations were at maximum amplitude when the universe became transparent. By analyzing this pattern, cosmologists can determine how much ordinary matter existed in the early universe and how much dark matter was present to provide additional gravitational pull that affected the oscillations. The results from CMB analysis indicate that the universe's total matter content is approximately 31% of the total energy density, with dark matter constituting approximately 85% of this matter, or about 26% of the total energy density. Ordinary matter contributes approximately 5% of the total energy density. These measurements are completely independent of measurements based on galaxy rotation curves or cluster dynamics, yet they agree remarkably well, providing strong evidence that dark matter is a real component of the universe. The CMB also provides information about when structures began to form in the universe. The temperature variations visible in the CMB represent the seeds from which galaxies and larger structures eventually grew. The amplitude and scale of these variations depend on dark matter's properties and its initial distribution. The observed CMB pattern matches predictions from models where dark matter is cold, meaning it was moving slowly in the early universe rather than at speeds close to the speed of light. Cold dark matter, or CDM, is distinguished from hot dark matter, which could consist of light, fast-moving particles like neutrinos. Hot dark matter tends to smooth out small-scale structure through its rapid motion, making it difficult for small objects like galaxies to form early in cosmic history. Cold dark matter, moving slowly, clumps together on all scales, allowing small structures to form early and then merge to build larger structures over time. The observed pattern of structure in the universe, with galaxies existing at high redshifts corresponding to early cosmic times, and with the distribution of galaxies matching predictions from cold dark matter simulations, provides evidence that dark matter is indeed cold. If dark matter were hot, the pattern of structure formation would differ in ways that are inconsistent with observations. The combination of CMB observations with other cosmological measurements has led to a standard model of cosmology called the Lambda CDM model. Lambda represents dark energy, discussed detailed later, while CDM represents cold dark matter. This model includes 6 fundamental parameters that determine the universe's properties, including the densities of ordinary matter, and dark energy. The success of the Lambda CDM model in explaining diverse observations has made it the foundation of modern cosmology.
Despite the strong evidence for dark matter from multiple independent observations, some researchers have explored whether the phenomena attributed to dark matter might instead result from modifications to our understanding of gravity. The most developed alternative to dark matter is modified Newtonian dynamics, or MOND, proposed by physicist Mordechai Milgram in the early 1980s. MOND is based on the observation that the discrepancies between observed dynamics and predictions from visible matter appear primarily in situations where gravitational acceleration is extremely weak.
In galaxy outskirts, where rotation curves remain flat rather than declining, the gravitational acceleration is typically less than about 1/10 billionth of Earth's surface gravity. Milgram proposed that Newton's laws of motion might break down in this regime of extremely weak acceleration. In MOND, gravitational acceleration does not decrease as rapidly with distance as Newton's law predicts when the acceleration becomes weaker than a characteristic value called A0, approximately 1.2 times 10 to the negative 10 meters per second squared. This modification causes gravity to remain stronger at large distances than Newtonian predictions, potentially explaining why galaxy rotation curves remain flat without requiring dark matter. MOND successfully reproduces galaxy rotation curves with remarkable accuracy using only a single parameter, A0, that is the same for all galaxies. This success is impressive and suggests that the phenomenology MOND captures is real, even if its theoretical foundation remains unclear. Galaxies of different sizes, masses, and morphologies all have rotation curves that can be fit by MOND using the same value of A0, which would be a surprising coincidence if MOND were not capturing some genuine physical principle. However, MOND faces significant challenges when extended beyond galaxy rotation curves. The theory must be modified to handle relativistic situations needed for cosmology, and various relativistic versions of MOND have been proposed, the most developed being TeVe's, or tensor vector scalar gravity. Even in these extended versions, MOND struggles to explain several observations that dark matter explains naturally. Galaxy clusters pose particular difficulties for MOND. While MOND can reduce the amount of missing mass needed to explain cluster dynamics compared to Newtonian gravity, it cannot eliminate it entirely. Clusters still require approximately twice as much mass as observed in stars and gas, even when MOND is applied. Proponents of MOND suggest that this remaining missing mass might consist of neutrinos or other particles not traditionally considered dark matter, but this requires adding components beyond the modification of gravity itself. The bullet cluster, discussed earlier, presents perhaps the most serious challenge for MOND. The spatial separation between the bulk of the mass, as determined by gravitational lensing, and the hot gas is difficult to explain in MOND without invoking some form of matter that behaves like dark matter. The lensing signal requires mass to be present where it is inferred from dynamics, and the fact that this mass is not coincident with the visible matter seems to require dark matter or something very similar.
The search for dark matter particles represents one of the most ambitious experimental programs in modern physics. Despite overwhelming evidence for dark matter's existence from astronomical observations, no individual dark matter particle has been conclusively detected in a laboratory setting. The search continues in underground facilities around the world, where scientists have built increasingly sensitive detectors to catch the faint signal of dark matter particles passing through Earth. The fundamental challenge in detecting dark matter particles is their extraordinarily weak interaction with ordinary matter. If dark matter consists of weakly interacting massive particles, or WIMPs, as many theoretical models suggest, these particles would pass through normal matter almost unimpeded. A WIMP could travel through hundreds of kilometers of solid rock without interacting with a single atom. Only extremely rarely would a WIMP happen to collide with an atomic nucleus in a way that could be detected. To observe these rare interactions, experimenters have constructed detectors containing thousands of kilograms of ultra-pure target material. The detectors are placed deep underground, typically a kilometer or more below the surface, to shield them from cosmic rays that constantly bombard Earth's surface. Cosmic rays would create backgrounds that would overwhelm any signal from dark matter, so the massive rock overburden above underground laboratories absorbs cosmic rays before they reach the detectors. Even underground, numerous sources of background exist that could mimic a dark matter signal. Natural radioactivity in the rocks surrounding the detector, in the detector materials themselves, and even in the experimenter's own bodies, produces radiation that must be carefully controlled and measured. Neutrons produced by cosmic ray interactions in the rock or by radioactive decay can penetrate shielding and scatter off nuclei in the detector, creating signals identical to what a WIMP would produce. To distinguish potential dark matter signals from backgrounds, experimenters employ multiple strategies. The detectors are constructed from materials selected for exceptional purity, with radioactive contamination reduced to levels far below what exists in ordinary materials. The detectors are surrounded by multiple layers of shielding, including lead to block gamma rays and polyethylene or water to moderate and absorb neutrons. Active veto systems surround the inner detector, using separate detector elements to identify and reject events caused by particles entering from outside. The inner detector itself is designed to measure tiny amounts of energy deposited when a particle scatters off a nucleus in the target material. Different detector technologies have been developed, each with particular advantages and disadvantages. Cryogenic detectors cool their target material to temperatures just a fraction of a degree above absolute zero, allowing them to detect the tiny temperature increase caused by even a single particle interaction. Scintillation detectors use materials that emit flashes of light when particles pass through, with sensitive photomultiplier tubes detecting the weak light signals. Liquid noble gas detectors, particularly liquid xenon, combine scintillation and ionization signals to identify and measure particle interactions with high precision. The liquid xenon time projection chamber represents the most sensitive dark matter detector technology developed to date. These detectors contain several tons of ultra-pure liquid xenon maintained at approximately -100 degrees Celsius in a cylindrical chamber. When a particle scatters off a xenon nucleus, it produces both immediate scintillation light and free electrons. The electrons drift upward through the liquid under the influence of an electric field, reaching a thin layer of xenon gas at the top of the chamber where they produce a second flash of light. By measuring both the initial light flash and the delayed signal from the drifting electrons, experimenters can determine the three-dimensional position of the interaction, the amount of energy deposited, and the type of particle that caused the interaction. The ability to distinguish between different types of interactions is crucial for rejecting backgrounds. When an electron scatters in the detector, caused by gamma rays or beta particles from radioactivity, the ratio between the scintillation and ionization signals differs from when a nucleus recoils after being struck by a WIMP or neutron. This difference allows electron recoils to be rejected, eliminating a major source of background. Distinguishing WIMP interactions from neutron interactions requires additional techniques, including measuring the distribution of interaction positions within the detector and the spectrum of recoil energies. Several large liquid xenon experiments are currently operating or under construction. The Xenon experiment, located in the Gran Sasso Underground Laboratory in Italy, has operated a series of increasingly massive detectors, with the current Xenon NT detector containing approximately 8 tons of liquid xenon. The Lux Zeppelin experiment, or LZ, operates in the Sanford Underground Research Facility in South Dakota and contains approximately 10 tons of liquid xenon. The Pandax experiment operates in the China Jinping Underground Laboratory, the world's deepest underground laboratory at more than 2 kilometers below the surface, with a detector containing several tons of liquid xenon. These experiments have achieved remarkable sensitivity, able to detect interactions depositing energies equivalent to just a few kiloelectron volts, approximately the energy of a single X-ray photon. The total background rate in the central regions of these detectors is less than 1 event per ton of target material per year over the energy range where WIMP signals might appear. This extraordinarily low background rate allows searches for WIMPs with interaction rates as low as 1 interaction per ton per year, corresponding to WIMP nuclon cross-sections of approximately 10 to the negative 47th square centimeters, more than 10 billion times smaller than the cross-section for a neutrino interacting with matter. Despite this sensitivity, no experiment has reported a conclusive dark matter detection. The observed event rates are consistent with expected backgrounds within statistical uncertainties. These null results place increasingly stringent constraints on WIMP properties, ruling out WIMPs in certain mass ranges with certain interaction strengths. As experiments become more sensitive, they exclude larger and larger regions of parameter space, narrowing the range where WIMPs might exist. The lack of WIMP detections has led some researchers to question whether WIMPs are the correct dark matter candidate, or whether dark matter interactions with ordinary matter might be even weaker than previously thought. Alternative dark matter candidates are being explored, including axions, sterile neutrinos, and various other exotic particles. Each alternative candidate requires different detection techniques optimized for that particle's specific properties. Axion searches use fundamentally different experimental approaches than WIMP searches. Axions are extremely light particles that would be produced in enormous numbers in the early universe, with individual axions carrying little energy. Rather than looking for individual interactions, axion searches look for the collective effect of many axions converting into photons in the presence of a strong magnetic field. The ADMX experiment, operating at the University of Washington, uses a high-quality microwave cavity placed in a powerful magnetic field to search for the faint microwave signal that would result from axion to photon conversion. The cavity is tuned to resonate at specific frequencies, enhancing the signal from axions with masses corresponding to those frequencies. By slowly varying the cavity tuning, the experiment can search for axions over a range of possible masses. The detector must be cooled to very low temperatures to reduce thermal noise that would obscure the tiny signal. After years of searching, ADMX has excluded axions in certain mass ranges, but has not detected a signal, though much parameter space remains to be explored. Sterile neutrinos, if they exist and constitute dark matter, might be detected through their decay into ordinary neutrinos and photons. Searches for sterile neutrinos look for characteristic X-ray or gamma-ray emission from regions where dark matter is concentrated, such as the centers of galaxies or galaxy clusters. Several observations have reported possible signals consistent with sterile neutrino decay, but these tentative detections remain controversial and have not been confirmed by independent observations.
Simulating the universe, computational models of dark matter and structure formation. Understanding how the universe evolved from the nearly smooth conditions observed in the cosmic microwave background to the richly structured universe we see today requires computational simulations that follow the gravitational evolution of billions of particles over billions of years. These simulations have become essential tools for testing dark matter models and for making predictions that can be compared with observations. The basic approach in dark matter simulations is to represent dark matter as a collection of particles, each representing a large clump of dark matter with mass typically millions to billions times the sun's mass. The simulation begins with initial conditions representing the early universe, with particles distributed according to the density fluctuations observed in the cosmic microwave background. The simulation then follows how these particles move under their mutual gravitational attraction as the universe expands. The computational challenge is immense. Even though each simulation particle represents an enormous amount of actual dark matter,
realistic simulations require billions or even trillions of particles to adequately resolve structure formation from cosmological scales down to galaxy scales. Computing the gravitational force exerted on each particle by all other particles would require a number of calculations proportional to the square of the number of particles, making direct calculation infeasible for large particle numbers. To make the calculations tractable, simulations use approximation methods that reduce computational cost while maintaining accuracy. Tree methods organize particles into a hierarchical structure, grouping distant particles together and treating them as single masses for force calculations. Particle mesh methods compute forces on a grid and interpolate to find forces on individual particles. Hybrid methods combine these approaches, using tree methods for nearby particles where accuracy is crucial, and mesh methods for distant particles where approximations are adequate. Modern simulations run on supercomputers with thousands of processors working in parallel. The simulation volume is divided into regions assigned to different processors, with particles moving between processors as their positions change. Sophisticated load balancing algorithms ensure that computational work is distributed evenly among processors, preventing some processors from sitting idle while others are overloaded. Even with these optimizations, large simulations can require weeks or months of continuous computation on some of the world's most powerful supercomputers. The output of these simulations is a detailed three-dimensional map of dark matter distribution at various times in the simulated universe's history. Researchers can analyze these simulated universes to study how structures form and evolve, to understand the properties of dark matter halos around galaxies, and to make predictions about observable quantities that can be compared with real observations. One of the most important results from dark matter simulations is the demonstration that cold dark matter naturally produces the cosmic web structure observed in galaxy surveys. Simulations starting from small density fluctuations consistent with the cosmic microwave background and following cold dark matter dynamics produce structures that statistically match the distribution of galaxies in the real universe. The sizes, shapes, and clustering properties of simulated dark matter structures agree with observed galaxy distributions, providing strong support for the cold dark matter paradigm. Simulations have also revealed universal properties of dark matter halos. Despite the enormous range of halo masses, from dwarf galaxy halos containing millions of solar masses to cluster halos containing quadrillions of solar masses, halos share similar density profiles and structural properties. The NWF profile mentioned earlier emerged from simulations as a universal description of halo density, though subsequent work has revealed more complex behavior, particularly in halo centers and outer regions. The internal structure of dark matter halos is more complex than simple spherical models suggest. Simulations show that halos are typically triaxial, meaning they are elongated in two directions rather than being perfectly spherical. The degree of elongation varies from halo to halo, but is significant enough to affect observables like gravitational lensing. Halos also contain substructure in the form of smaller halos that have been accreted and survive as distinct objects within the larger halo. This substructure is particularly interesting because it represents the predicted population of dark matter halos that might host satellite galaxies around larger galaxies like the Milky Way. Simulations predict that halos the size of the Milky Ways should contain hundreds or thousands of subhalos massive enough to potentially host small satellite galaxies. However, observations show only a few dozen satellite galaxies around the Milky Way, creating what is called the missing satellites problem. Several possible solutions to the missing satellites problem have been proposed. Perhaps most of the predicted subhalos are dark, containing only dark matter without sufficient ordinary matter to form stars and become visible galaxies. The physics of gas and star formation might prevent small halos from forming stars efficiently, leaving them invisible. Alternatively, the discrepancy might indicate that dark matter has properties not included in standard cold dark matter simulations, such as interactions that suppress small-scale structure formation. Simulations have also been used to study how ordinary matter interacts with dark matter and how galaxy formation proceeds within dark matter halos. These simulations, called hydrodynamic or cosmological simulations, include not only dark matter, but also gas, star formation, and feedback processes where energy from stars and supermassive black holes affect surrounding gas. The inclusion of these baryonic processes adds enormous complexity, as the physics governing gas behavior, star formation, and feedback spans an enormous range of scales, from individual stars to entire galaxies. The Illustris simulation, completed in 2014, was one of the first large cosmological simulations to include sophisticated treatments of baryonic physics. The simulation followed both dark matter and gas in a cubic volume 106 million light-years on a side, with enough resolution to study individual galaxies. The simulated universe produced galaxies with properties broadly similar to real galaxies, including realistic colors, sizes, and morphologies. Subsequent simulations, including Illustris TNG, Eagle, and others, have refined the treatment of baryonic physics and expanded the range of processes included. These simulations can now reproduce many observed properties of galaxies, including the relationship between galaxy stellar mass and dark matter halo mass, the sizes and structures of galaxies, and the chemical composition of galaxies. The success of these simulations in matching observations provides confidence that our understanding of structure formation and galaxy evolution within the dark matter paradigm is fundamentally correct. However, challenges remain. Simulations still struggle to simultaneously match all observed galaxy properties, particularly for dwarf galaxies and massive elliptical galaxies. The simulated galaxies sometimes have too much star formation in their centers or not enough in their outskirts compared to observations. The properties of satellite galaxies around massive galaxies do not always match observations precisely. These discrepancies might indicate missing or incorrectly implemented physics in the simulations, or they might point to issues with dark matter models themselves.